Okay, so we'll get started. Okay, so we'll continue this discussion from last Tuesday. And then now I just want you to focus on the board over here. Remember we talked about we can calculate the E cell by looking at the difference between the standard electrode potential of cathode and anode. Okay, so because that's the convention, the way it works, the way the electrochemistry community is structured, we put cathode first and anode. Okay, so this is a little different than the way I tell you guys how to memorize what happens interface of electrode and your electrolyte solution. So when the E is positive, this reaction is feasible. Otherwise, it's the other way around. So here the standard electrode potential that is measured against to hydrogen. We set hydrogen to be 0. Sometimes you will see in the literature there is acronym like HER. Okay, that means hydrogen evolution reaction. When there's a redox process happening, when the potential is high enough and when there's water, electrolysis of water happens. So that means you're generating oxygen and hydrogen from water. And the last time I briefly mentioned the environmental application, rusting, which means the iron 0 going to become being oxidized to the copper 2 or copper 3, okay? Actually, every year there's a very high number of steel production, and this is used to replace the rusted steel or iron that is used commercially. Usually people will use a more active metal so that the rusting process of iron can be slowed down. Okay, so in the rusting process, iron in fact functions as a cathode and an anode. First, it will give away electrons, right? So when we think about these metals, I mean the electron is far away from the nucleus, right? So from the Coulomb's law, we know that the farther away you're from the nucleus, the electrostatic interaction is smaller, right? When the electron is available, it injects the electron to the interface, and at that interface, we can react with oxygen, and then you form water. Okay, so if we have a complete, we can balance this equation. So generally, you're using water, oxygen, and iron to complete your redox cycle, and then you generate iron oxide, and that is this brownish red stuff that you will see at the surface, and it decreases the mechanical property of your steel. Okay, so when there's a more active metal is present, then iron function more like a what? More like a cathode, right? So we can figure that out by looking at the difference. The lower the value, the standard electrode potential value, the more active this metal will be, right? So if you don't remember that, you can use this equation and to figure it out what's going on. And so when you are dealing with redox reaction, it's very important to actually write out the oxidation number so you do not get confused. Because a lot of time, even when I was studying this, I know this is the oxidant, I know this is a reducing agent, but in the process of thinking and doing the problem, sometimes you will mess it up, and then you would not get the right answer in the end. Okay, so when these metals are present nearby the iron or as a coating for your iron, it will slow down the rusting process. And then there's some fact listed. There's numerous fact listed in your textbook about this process. And I just want to mention in ionic solution. So think about ship that is sailing on the ocean, right? There's a lot of salt, right? So generally, salt is known to accelerate such process because we're thinking about a redox process. In the pure water, the conductivity is quite low, right? So in the salt water, so the solution will become more conductive when you have more salt in it. So in the presence of a high ionic strength solution, the rate of rusting process will increase. Another case is that we don't really have that problem here in Taiwan because we don't have a lot of snow in the winter time. But in the United States and Europe, when they get a lot of snow, they will put a lot of salt like calcium chloride and other kind of salt on the road. Okay, so we know from the chapter 13, when we have salt, what would happen to the melting point of water? Melting point suppression, right? Because these salt will participate in the nucleation of water as it changes from liquid state to solid state. So when you depress the melting point by several degrees Celsius, then you won't have a lot of snow on the road. So of course they physically remove the snow, but that residual amount of the snow could be dangerous because you think about car running over a road that has snow on it, what does the pressure would do to the snow? It will lower the melting point because we know pressure has some effect on the melting point. And then you get a slurry, so that means you get an ice and water mixture, so that reduces the friction between the tire and the road, so that could be dangerous. Okay, so that being said, salt are put on a road, so a lot of time, especially places where they get heavy snow in the winter, so sometimes the snow season could be as long as 6 to 7 months. So like in May, we will still get snow in some location in the United States. So they use a lot of salt, and that creates one big problem for your car. So under the bottom of the car, even there's anti-corrosion coating. Like I said, there's different kind of metal are present. Generally, the condition of car won't be very good because the bottom of it is slowly rusting. Maybe it looks fine when you inspect it, but there's a lot of channel for these salt and then for this redox process to happen, to take place, so that inside your car, there's a lot of rusty place. And then so one notable place is where you open the door, the car door, you will see rust slowly forming after a year or 2 years when you own a car. Okay, so of course, you can use some chemical solution that you bought from the store to remove that rust, which will also slow down the redox process because generally these solution will contain some sort of additive that will create a coating and which protect your underlying metal. So besides using these metal, I also want to point out in the native state of these metal, they oxidize quickly. Okay, so on the surface of these metal, it's not pure metal. You also have an oxide layer. So how are the quality of these metal will also affect such process. And I want to mention that for more advanced application, alloy is used. So everybody remember what alloys are? So alloys are a mixture of metal. So a common one would be gold, cadmium with copper. Okay, so it's a mixture, the ratio of these, and then the smoothness of such coating will affect the appearance and property of your coating. And I just want to mention that cadmium is very toxic. So in the old days, it's allowed to use this because this is the process that people first figured out that works quite well. But now cadmium is being banned from a lot of countries. And another one like zinc is very cheap, right? So you will see zinc alloy with cobalt or even with iron and nickel as a surface coating. Okay, so how is this redox process important? In about 1800, there's a French scientist discovered you can actually deposit silver iron onto an electrode because before that, people don't know how to use electricity. So I find it amazing. It's only, the whole process is only known about 200 years ago when people first figured out how to use electricity. Okay, so in the early 1800s, a scientist figured out you can deposit silver iron onto a metal surface and which create this very shiny, beautiful surface. But it's not until 1840 people actually industrialized such process because they found that potassium cyanide can be a great electrolyte for this purpose. When we're thinking about redox process, I know we didn't really touch on the formation of complex, metal ion complex in solution, but you have to recognize that as the ion is being reduced, the ion is not a naked ion. It's not just iron plus 2 or silver plus 1 in the solution. There are ligands, okay? So for example, think about Lewis acid, Lewis base. So water can act as the ligand for a lot of metal, right? So for the metal to be reduced from a solution state to the solid state, the ligand has to come up first. In that electrolyte solution, it may not be simple as just pure water. You're gonna have different kind of salt where you have as an electrolyte, and these salt, they have different kind of binding strength to your metal ion, okay? So it's a very complex process. So first, the ligand has to dissociate, and then the electron has to be transferred to the ion. So when it gains an electron, it will become reduced, right? All right, so then this process, like the voltage that you use and the concentration, it all matters. Because like I said, the roughness is a very important parameter to control the surface property. So if you dip a metal, you employ your metal as an electrode and you dip it into a solution that has electrolyte and then the ion that you desire. So you can, under certain condition, you can do electroplating. And then so in Europe, there's a lot of beautiful silverware. So back in the day, the utensil, the fork, the knife you use, they were actually coated with silver. And that technology is transferred to China, so people were able to create all these beautiful art pieces by electroplating. However, this industry is a very heavily polluted because think about all these toxic electrolyte and the metal ion that would be present in a solution. How would you discharge it would be very difficult, but back in the day we don't know better, so usually they are discharged into rivers and oceans. So why do we need to do electroplating? The first reason is we want to protect our metal, and second is we want to have some surface property or even change the mechanical property when you can deposit a certain amount of alloy material onto your surface. And also sometimes it's just for the appearance. Okay, so nobody wants to buy a dull looking structure, right? We like our structure to be shiny and pretty. Okay, so now we will get to some introduction of battery. This is just a name for, remember we talked about a voltaic cell? Okay, so a different name, all right. So let's go through a couple type of battery, and these are just common knowledge, and I won't have a lot of questions, like very specific question, say, okay, what the lead acid battery is all about. I will ask very specific question, more focused on the concept, okay? But these are just the common sense that you need to know. So there are two types of battery. One is the one that you just throw away. These are called primary battery. And the other type are called rechargeable battery. They're made out of different material. And of course, the costs are different. So let's go through some of the battery. So there are several kind of battery, right? So the most common one is the one on the far left. You get a lot of these type of battery, and they have different size. But that means they can store different amount of electron, and generally their voltage is limited. In order to bump up the voltage, they have to be specially engineered. So the way that the cell is structured, you can obtain different voltage. So, and then of course, it comes down to the resistance of your circuit and how much electron, how much work you need the electron to do, and now the voltage will determine that process, but this is a whole nother story. But anyway, for a standard cell, it's based on the manganese, so it has manganese oxide, and then so zinc chloride and the ammonium chloride paste is used as the electrolyte. So actually you have the middle part would be your cathode, and then the outside part is your anode. So as the redox process happens, when you put it into a circuit, the electron will flow from anode to cathode, but the way it is set up, you may get a positive sign or negative sign, okay? So do not get confused by the plus and minus signs. Focus on what happened to the oxidation state. Okay, so because the definition in electrical engineering is very different than the electrochemistry, okay? Anyway, okay, so then the bottom battery is commonly found in your watches, right? Nowadays, if you think about people talking about lithium ion battery, so in a lab when we're doing testing, because this is a very simple device structure, basically you have a container and then you put your electrolyte in, and then just cap it, and then it becomes a device, a battery device that you can test for its charge cycle. Like I said, the device structure will dictate how well this battery works. And this is why the manufacturer will say how many times this battery can be charged. So generally, the amount of charge that can be stored versus the charge cycle, so it will generally decay over time. So let's say when you charge the battery, you reverse the reaction. However, you did not reverse that reaction completely. So each time, the amount of electron can be harvested or utilized decrease. All right, another type of this is called the lithium iodine battery. And of course, people are searching for different kind of lithium-based battery, because if you think about electrical car, you don't want to charge it all the time, right? It be able to run for more than 300-400 kilometers before you have to charge. But of course, it's a little different for Taiwan because we don't have to travel a long distance. But in like Europe and US and China, the distance between cities are very far. So people care about the distance that the car can travel. So if you are using a lot of inefficient devices like these small battery, you will need a lot of battery to be able to support your car. So nowadays people are looking for high power density battery. That means they want it to be smaller and lighter, but hold a lot more usable electrons, right? So a lot of people are working on the various type of lithium battery, but we know lithium is very reactive. So if this device is not properly stored or properly operated, the lithium might come out and then cause fire hazard. So there's different type of lithium battery, such as right now, one of popular one is called the lithium sulfur battery. So that actually involves the redox cycle of sulfur and lithium. And there's also lithium air battery. So it utilizes oxygen. So you let small amount of air in, and it utilizes the oxygen to undergo the redox process. Let's go through some specifics of each type of cells. I think by now you should be fairly familiar with which is cathode, which is anode, by recognizing what is present, okay? So the overall reaction, I know this looks a little different than what you would see because this is the introductory course. Here, the ammonium chloride is actually participating in such a reaction because it functions as a ligand for your metal. Like I said, this is a very low voltage, and then the voltage, what dictates the voltage? That, right? So the difference of the metal, the difference in their standard electrode potential will determine the potential of your cell, okay? So such process is limited at 1.55 volt. So it's fairly small compared to the electricity that we normally use, which is at 110 volt, right? Okay. And then there's a different type called the alkaline battery. Okay, so why is alkaline? Because it has hydroxide in it. So that's where all these names come from, okay? So again, for the bottom battery, I mean, this is the old process. It used mercury, which is a very toxic metal, and people are working on trying to avoid or reduce the usage of such toxic metal. But back in the days, it's not a big issue. So people developed this technology. You basically use zinc and silver oxide. So even though we call them dry battery, but they actually have very small amount of water present in this cell. And then this is why when you store the battery in a very humid place, the rusting process will take place, and sometimes you will see some white precipitate or white solid on the outside, right? So these are the electrolyte coming out from your battery. Okay, so for lithium battery, look, the voltage is much higher, right? So that means you have higher driving force for lighting. For example, for a 3.5 volt battery, it can power more LED bulb than the 1.5 volt. So here is a picture. It sounds scary. We are putting lithium metal into your body, so because it can supply a lot of energy. For people with heart issue, pacemaker is normally used. And nowadays there are implants that you can put in and last for years. And then for a lot of low power requirement electronics, they can later be powered by battery. And nowadays you get one sub area is called flexible electronics. So people are looking into how can we make battery flexible. This is a very hot topic in the research field right now because most of the time batteries are made of these rigid structure. And then you don't want to carry a big pack of battery around all the time. So we want something flexible and something that's safe and also inexpensive. So that's why people are still working on battery, even though it has been around for many, many years. And now we're talking about a different kind of electrode, the cadmium nickel battery. It has higher power density than the previous one. And generally these are rechargeable. And then sometimes you will see, this is the newer version, so you get the metal hydride battery. So like it says, the capacity is a little higher, okay? Lead acid battery. So this is the big battery that you will normally find in the cars. They have much higher voltage based on lead. So it actually utilizes sulfuric acid as the electrolyte because we know that the strong acid can dissociate. And then the lead serves as an anode, and then this is the redox process present in the lead acid battery. And so when we connect our battery in series, we can increase its voltage. So when we turn on the car, we're actually charging our battery. We use the battery to begin our engine. And then so if you leave your light on, eventually the battery will die and then you will need someone else with a charged battery to help you out, right? So we call the road rescue. So how does this work? So when you have a battery that is essentially, if you connect it to a working battery, so that means it has higher potential, right? So it's out of its equilibrium position. So when you connect it into circuit, the working battery will continually putting electron into the dead battery. And then you reverse the anode and cathode, going from a charging process, going from a discharging process, which means give off electron, to a charging process at the dead battery. That makes sense? Okay, another type of battery, like I mentioned, hydrogen fuel car. So hydrogen, the fuel cell actually been around for about maybe 50 years now. So when we first send a satellite to the outer space, fuel cell is already being used. So that is like from the 60s. People already have this technology. But people continue to work on such process. So remember, for a battery to work, it needs a salt bridge. But in the battery that you saw, it's engineered different than the very ancient, these redox system that we have, right? So it's engineered in the case that we need a separator inside the cell. It's sort of some function as a salt bridge. So for the hydrogen fuel cell, as you can see, you're using hydrogen as a fuel, and then this is regarded as a green energy, or sometimes you will hear hydrogen economy. So basically, we hope we can use solar cells that harvest solar energy. Then you have a flow of electrons, so you can undergo electrolysis of your water. You can separate that hydrogen out and take its chemical energy by using hydrogen fuel cell. And it's a very simple diagram, but there's many components in it. Okay, so There are a lot of faculties in Taiwan or in US who is working on more efficient catalysts to catalyze such redox process, because you think about you have to get the gas phase hydrogen in, and then when they contact with the electrode, you have to break that bond and then turn it into proton. Okay, so for fuel cell, there are actually two types: the alkaline fuel cell and the acidic fuel cell. Because recognizing that sometimes we use OH minus and sometimes we use proton, so it really depends on your electrolyte pH. Now we're moving on to electrolysis here. Okay, so this is to drive chemical reaction. So a very common example using molten salt. So this is a high temperature process, and so you increase the temperature, and eventually it melt, and then these reactant also function as an electrolyte in such system. So when you put the electron in, the anode and cathode are both doing reaction. So this is a little different than the voltaic cell, okay? So for the voltaic cell, output the energy. So we'll discuss more when we talk about thermodynamics, because for now you just have to know for voltaic cell, it gives off energy. And for electrolytic cell, for the reaction to happen, you putting energy, because think about when you generate electricity, you need to burn fossil fuel, right? So you get that energy from somewhere else, from the chemical energy, it turns into electrical energy, and then you put it into your reaction, use that electricity or electrical energy, and you convert it to chemical energy, because you're forming bond, you're breaking bonds, right? And then when you get that surplus of energy, something happened, right? Okay, this is a very classic process that allows for the making of sodium hydroxide. Once you generate sodium, you'll react with water, and it also generates chlorine. Right now with the COVID-19, people use the sodium hypochlorite as a disinfectant. So for that, when people are talking about 电解氯酸水, so that is similar process happening. They generate the chlorine and then they oxidize the chlorine by the electrolysis, okay? So we already seen this so many times. So if there's no other reaction that is as efficient as the electrolysis of water, the hydrogen evolution will take place. So normally, when people are conducting a failed experiment, well, unless that is their goal to produce hydrogen, a failed experiment is you're just converting water into hydrogen. It's a competing reaction to the actual reaction you want to do. So how do we get aluminum? In nature, aluminum are present in its oxide form. We will actually use a lot of electricity to do such process. This is aluminum oxide, right? And then this is the process that are still used. So some other people will look at the type of electrolyte that is needed. Okay, so if you look at such process, we use carbon as a reducing agent to harvest aluminum from its oxide. Okay, let's look like a different case. So you can actually do organic reaction. This is a very popular field in organic chemistry, so that you combine electrochemistry with photochemistry along with the traditional organic chemistry. So you will later run into different kind of oxidant and the reducing agent, right? So in organic chemistry, these are the process responsible for making and breaking bonds. So essentially, you can actually directly put the electron in. There are still some new papers on how can you use electrochemistry to efficiently make the molecule that can be made in the same way before. In this case, you can see you can turning acrylonitrile into something else. And then these are important building blocks for making polymer, okay? So, but I just want to show you more of the battery system. So this is a picture when we show your reagent as these little blobs. So initially, these are ions, and then they undergo these complex processes and eventually you get chlorine and hydrogen. So it really depends on the condition, then you can enable, or you would have different side reaction if these are not what you desired. Like I said, the molten sodium chloride, you can also do this what's called the mercury cell. So mercury, we know, is a liquid, right? It's conductive, it's a metal. So it can actually be used as a electrode for electrochemistry. So here is, you put the water in, right? And then this whole thing is your electrode. So you can read through this, and this is what's happening. So it's actually much more complex than it looks when we have a simple reaction, right? So actually, the electrode is also participating in the reaction, but this mercury can be recycled. And then here's some discussion. It's on the more practical side of these type of processes. Look, the 3,400 kilowatts per hour, so that's a lot of energy. But when you employ a diaphragm cell, it's a little different. And so there's another setup. You can use a membrane for such process. So very similar to the ion selective membrane that I previously mentioned. So these can be inorganic material, organic material, or a mixture of both. Okay? So I think that's all I have for today.